All right, let's get into it. Today, we're not just going to learn about a topic. We're going to go on a journey. We're going to explore one of the most fundamental ideas of our time, information theory. But we're going to do it in a really cool way, not through some stuffy textbook, but by looking through the pages of a very special diary.
So this is our guide, A Diary on Information Theory. It was written by the Hungarian mathematician Alfréd Rényi. And let me tell you, this is not your average academic book. It's really more of a work of art, designed to take something that sounds super complex and make it feel totally intuitive.
And this quote from the beginning of the book, well, it says it all. This is Rényi's whole philosophy. He truly believed that math wasn't just some tool you use to get a job. For him, it was this incredible source of joy and beauty, something you should share. And that's exactly the spirit we're diving into today. Now, to share this love for the subject, Rényi does something pretty clever. He doesn't just lecture at us. No, instead, he tells the whole story through the eyes of an imaginary university student, someone who's learning about information theory for the very first time, just like we are. And here we go. We're opening up the first page of the diary. Our narrator, the student, he's just come out of his first lecture, and he's so fired up that he decides he's not going to take regular notes. Instead, he's going to keep a diary to capture his own thoughts, his questions, his aha moments. So we get to learn right alongside him from day one. The class kicks off with this massive idea. Information isn't just about computers or books. It's everywhere. It's in our DNA, it's how our brain works, it's how we guide a spaceship. But then, the lecturer throws out the real challenge. Can we actually measure it? Can we put a number on information, the same way we measure distance in feet or weight in pounds?
So, how in the world do you measure something you can't even see or touch? Well, the lecturer doesn't start with some crazy formula. He starts with a game. A game I'm pretty sure we've all played before, 20 questions.
So he poses this little puzzle to the class. Picture a room with 32 students. I'm thinking of one of them. Your job is to figure out which one, but you can only ask me yes or no questions. What's the fastest way to do it? What's the absolute minimum number of questions you need to be sure you'll get the right answer? And our student narrator figures out the strategy right away. The most efficient, the perfect question is always the one that splits the remaining possibilities exactly in half. So your first question takes you from 32 down to 16. Your next question, from 16 down to 8. And you just keep doing that, having it again, slicing away the uncertainty until there's only one person left. And there it is. The answer is 5. It takes exactly 5 perfect questions. And here's the kicker, the big idea. That number, 5, isn't just the answer to a brain teaser. In information theory, that number is the amount of information. We've just put a number on it. We've measured it. Okay, so we've seen the logic. Now let's see how this simple idea from a classroom game actually gives us a universal, scientific unit for measuring information itself.
And that unit is the bit. A bit, short for binary digit, is the amount of information you get from the answer to a single yes or no question that cuts the uncertainty in half. It's like the fundamental atom of information. Every time you get an answer, boom, you've gained 1 bit.
But this is where things get really interesting and maybe a little weird. To really hammer the point home, the lecturer poses another question, one that's designed to kind of mess with our everyday ideas of what information means.
I mean, look at this. It's a brilliant example. One question is totally trivial, right? The other could change your entire life. But, and this is the key, in the cold, hard logic of information theory, if they're both just yes or no questions, they contain exactly the same amount of information, 1 bit. Mathematical information has nothing to do with meaning or importance. It's just about reducing uncertainty.
So, okay, we've got this great intuition from the game. We've got a unit of measurement, the bit. What's the next logical step? Well, you turn that logic into an elegant mathematical formula.
And here it is. It's known as Hartley's formula. It basically says the amount of information you need in bits is the base 2 logarithm of n, where n is the total number of possibilities. And let's just check it with our example, right? What's the log base 2 of 32? It's 5. The formula works perfectly. It's just the game, but in math form. And what's amazing is how this scales up. The lecturer gives this real-world example from Hungary at the time. To identify any single person out of about 8.4 million passport holders, how many bits would you need? Well, you plug that huge number into the formula, and the answer comes out to be just 23. Wow! The identity of any person in a whole country can be pinpointed with only 23 bits of information. So the lecture ends, and our student feels like he's totally got it. But then, as he starts writing in his diary that night, the real magic happens. Because those simple answers he got in class start leading him to much, much deeper questions.
First, he starts to wonder. The 20 questions game works perfectly if you ask perfect questions every time. But what about in real life? We ask dumb, clumsy questions all the time. What happens if you ask a question that gives you information you kind of already knew? And he figures it out. The information from a clumsy question just overlaps. It's redundant. You don't get a full, fresh bit of new information. It's like some of the information you just got is telling you something you were already told. That wasted part of the bit, it just disappears. You get less value. But that idea leads him to an even weirder, more profound question. Hartley's formula is great when you have 32 choices, because log base 2 of 32 is a nice whole number, 5. But what if you have, say, 7 choices? The formula gives you an answer of about 2.8. But what on earth is 2.8 bits? You can't ask 2.8 questions. It sounds like nonsense. And after really wrestling with it, our student has his own breakthrough. That fractional number, 2.8 bits, it only makes sense if you think about it as an average. If you played the game with 7 items over and over and over again, sometimes you'd get lucky and guess it in 2 questions, sometimes it might take you 3, but on average, over the long run, it would take you about 2.8 questions each time.
And this is where the diary leaves us, at the end of day 1, with this absolutely mind-blowing final thought. If we can measure information with the same kind of mathematical rigor we use for things like distance or time or mass, well, does that mean information isn't just an idea we invented? Could it be a real, fundamental, physical part of the universe itself? Now that's a question to chew on.